Okay, so today I have the following plan. I want to talk to you about the thermodynamic limit of the deep vinegar model. We will do essentially move towards the thermodynamic limit, how you rewrite the equations in terms of integral equations. We'll discuss the ground state a little bit, we'll discuss simple excitations, and then if I have the time I will actually work you through the equilibrium thermodynamics of the model, producing the Yang-Yang formalism for the thermodynamic beta ansatz. And then we will see how we do. Were there questions about the first lecture yesterday? I see that you have received the notes, so hopefully that complements what we did yesterday. So were there questions, interrogations, nightmares you had yesterday, or whatever? No? Okay, so then we can just get going. So let's do that. The thermodynamic limit. I don't always like calling it the thermodynamic limit because there's nothing thermal to it. It's just the infinite size limit. It's not a continuum limit either. We're already in the continuum. So it's really the infinite size limit of finite density. So let's call it the thermodynamic limit, like everybody. Okay, so we've seen the beta equations for our system. Now the solutions to the beta equations, we said, could not be obtained in closed form for generic choices of quantum numbers. There are, however, some characteristics of the solutions to the beta equations that you can very simply highlight. So let me just start by highlighting one of these things. So just a little definition here. Little function we'll be using quite a lot. We will take the derivative of the scattering kernel that we had as a fundamental function. So we have this theta of k right here. So its derivative is just a Cauchy distribution. So 1 over pi c divided by k squared plus c squared. Okay, and that I will write as this curly c of k. So this function here just tends to the delta function when c goes to 0, and it will appear in many of the equations that we have later. So one of the things about this function, of course, is that it's bounded. So you can just see that for positive values of c, this kernel here for any value of k is just between these two boundaries, 2 over c. Okay, so for all k included in the real numbers, we can just write such a thing here. Okay, so why do we do that? Well, okay, let me just write another inequality here. You can just reintegrate this thing here to give an estimate for or a bound for the difference between the scattering kernels that we have for two rapidities. So phi k1 minus phi k2, this is of course a combination of functions that cannot take arbitrary values, so this is just the integral from k2 to k1 of this c. And this you can just immediately bound by 2 over c, k1 minus k2. Okay, so why are we doing that? Well, simply because if we substitute this in the beta equations, we can obtain a bound for the differences of rapidity. So let's just consider the absolute value of some kj minus kl. So because of the beta equations, you remember there were just the k plus the summation of the phases. And these phases, so the whole left-hand side of the beta equations was a monotonically increasing function of k. Okay, so necessarily the difference between the quantum numbers has 2 pi over L times the difference between the quantum numbers has to be larger than the difference between the associated rapidity. So we can immediately write, very simply, 2 pi over L, absolute value of ij minus il. Okay, this can only be greater than or equal to the difference here. So already the differences between the rapidities is bounded once you fix the difference between the quantum numbers here. Now this estimate here allows us to write inequality the other way, because then we can just estimate the contribution from the scattering terms to the beta equations. And essentially what happens is that you just bound it this way, and then you count the number of terms that you have. The number of terms that you have is just n okay, because that's the number of particles you have, so you have this n over L. So essentially what you can write is that also the difference between the rapidity, so these quasi-momenta, has to be greater than or equal to, again, this difference between the quantum numbers. But then there's a little correction here that comes from this estimate here, so this is just 1 plus 2 times the density that you have divided by C. Okay, so just a very, very simple inequality, or a pair of inequalities, that gives you the range in which the differences between the solutions of the Bethe equations can vary for a given value of C and a given finite density. Okay, so you remember a little n, which is big N over L, it's the linear density of particles that we have in our system. Okay? So what this tells you is that when you go to the limits of an infinitely large system at a finite density, the distances between the rapidities becomes of order 1 over L if the quantum number difference remains of order 1. That means essentially that the distribution of these rapidities on the line becomes essentially a function that you can identify with a smooth function. Okay? So that we will exploit. Okay? So what we will do is essentially do the following. So let's view ij over L as some coordinate xj on the real line. Okay? So there's a quantum number space, which is just R, okay, which we will use as the kind of label for our quantum numbers. Now, what we can do is essentially rewrite the Bethe equations in the following way. What we will imagine is that there's a function k of x, okay, which when evaluated at the points xj corresponding to 1 over L times the quantum number, gives you the solution to the Bethe equation. Okay? So what we will rewrite, what we will do is rewrite our Bethe equations in the following way. Okay? Okay? So if you want, the thing that we impose is that k of xj is by definition kj solving the original Bethe equations that we have written last time. Okay? So it's just a rewriting. Now what we can do is essentially introduce a density which we will write as rho of x, which is 1 over L summation over all the quantum numbers that you have of delta of x minus ij over L. Okay, so given a proper set of quantum numbers, you have a well-defined distribution rho of x, right, which is defined according to this summation. So what this allows you to do is to rewrite this equation in a slightly different way. So you extend the definition of k of x to the whole line R by requiring that k of x plus now the integral from minus infinity to infinity dy of phi of k of x, one parenthesis too many, minus k of y, rho of y is equal to 2 pi x. Okay, so we've done a conceptual step here because we have started with a set of quantum numbers, ij. We have imagined that, we have solutions to beta equations that give us the kj. We have defined the points of a function k of x only at these isolated points. We've defined the value of this function at these isolated points. And then we say what we do is that we continue the definition of this function to the whole real line by requiring that this function k of x satisfy this equation here. This is a choice. This is an input we make. We could have done that in an infinite number of different ways. This is one way, okay, but we choose this one. Now, of course, this is just a linear integral equation for k of x, and it will have an explicit solution provided you input a row of y. So row of y is essentially the place where your labeling of eigenstates is now hidden. So you give me a row of y. In other words, you give me a set of quantum numbers, and then I will give you a k of x on the whole real line. Okay, so it's just the way we do it. So we now think of not labeling our eigenstates anymore in terms of discrete sets of quantum numbers, but rather in terms of kind of function label. So now the label for our eigenstates is row of x. Okay? Now, you can view this in different ways. You see, so the x here now takes all values on the real line. Now, if you have a certain system with, say you're interested in a system with an even number of particles, then you know that your quantum numbers have to sit on a particular lattice, right, of the half-odd integers. Now, in your eigenstate, you choose occupied quantum numbers, but equivalently, you choose unoccupied quantum numbers. So there are loads of positions, loads of acceptable quantum numbers that are left unoccupied. Okay? Now here, this equation here defines the value of k also for the unoccupied quantum numbers. Okay? You understand what I mean, right? So for a given parity of the number of particles, your quantum numbers fit on a certain lattice. Now, this function here goes through the value of the quantum number that you require at the point where, this k takes the value of the solution to the beta equations. But it also goes through the values of the positions of where you could have had holes. So you can associate quasi-momentum to holes as well via this definition. Okay? So in a sense, there's a hidden function here which is not written, which will be a density of holes, okay, which we will just meet in a couple of minutes. Okay, so what we do really is that we define other densities okay, the first one is this density of hole of x, 1 over L, okay? And now the way you didn't receive the printouts of today's notes yet, right? Okay, so maybe I should just be, let me write it and then define the sets that are here. Okay, so there's a summation over n in what I'll write the set of I tilde. So these are the quantum numbers that are occupied by holes. Okay, or the quantum numbers that are left empty. So again, there's just the delta of x minus this n over L. Okay, so I are the occupied quantum numbers. So they are the particle quantum numbers. I tilde are the unoccupied. So these are the whole quantum numbers. Okay? So this row hole of x is simply the density of occupation of holes in the space of quantum numbers. So there's this row hole function here, and there's of course also a row total function of x, which is 1 over L, the summation over n in the union of I plus I tilde of delta of x minus n over L. Okay, so the row total of x is kind of a trivial function because it's just a comb of delta functions on the appropriate lattice, going from minus infinity to plus infinity. Okay? We have the simple identity that rho of x plus rho whole of x is equal to rho total of x. Okay? And if you want the thermodynamic limit, so let me write it just like this, maybe limit thermodynamic, of rho total of x, this goes to 1. Okay? Because what you have are just delta functions at spacing 1 over L. Okay? And essentially any smooth function that you have, which has any measure of differentiability on a scale of 1 over L, will be such that when you manipulate it, you do anything with it, the rho total will just behave as the unit operator in this functional space. Okay? But of course, you have to be slightly careful with this. Some of the subtleties of the thermodynamic limit. Okay, so this rho total function in the quantum number space is just unit. But the rho x and rho whole, they can vary. Okay? Of course, the rho plus rho x, these densities, rho, it's a positive definite quantity. Okay, so it takes values between 0 and 1 in the thermodynamic limit. Rho whole, the same thing. Okay, and the sum of the two is just 1. Now, there's one important aspect of this equation here, is that really you can view it as a mapping between two spaces. You can view it as a mapping between the space of quantum numbers and the space of rapidities. Okay? It defines a map. And this map turns out to be one-to-one and onto. It's invertible. Okay? So what you can actually, let me maybe give a number to this equation, or maybe I don't need that. Okay, so k of x is a mapping between the spaces for x and k. So let me just write it like this, the abuse of notations. It's a mapping between the two spaces. So actually what we can do is rewrite our equations equivalently in rapidity space. Okay, so when I say rapidity, I mean these k's. Okay, so quasi-momenta, rapidity, same thing. Okay? So we have a function x of k. So equivalently, we have x of k. Okay, so the inverse of this mapping is just x of k. You can view it one way or another. Okay, now we can move to k space, defining densities. Now, rho of k, so be careful here because it's an abuse of notation. I use the same symbol, rho, for a new function. Okay, it's differentiated from the old function, but just by its argument. This is rho of k. It will now be a density of particles, but in rapidity space. Okay? And because we've defined the density in terms of these delta functions, and we know the transformation rule for delta functions, we can write this rho of k simply as rho of x of k, right, with dx of k dk. So provided we know the k of x function, we know the x of k function, therefore we can do this transformation here. So the same thing, this is also the same transformation rule for rho whole. So this one is just going to be the rho whole of x of k. with dx dk. Okay? And the rho total, so rho total of k, if you work it out, you remember that rho plus rho whole was rho total in x space, and rho total in x space became 1. So this one, rho total of k, just becomes dx of k dk. And we still have rho of k plus rho whole of k is equal to rho total of k. But now, rho total of k is not equal to 1. It's a function that varies with k. It's the density of available rapidities, if you want, either for particles or for holes, for a given state. Okay, so this is just a complete rewriting of what we have. Now, the beta equations you can rewrite in the following way. So now, k, if you want, is the source. So you can write k plus the integral from minus infinity to infinity dk prime phi of k minus k prime rho of k prime is now equal to 2 pi x of k, right? So now k is like the source term for the function x of k, okay? Given a certain problem. Okay, so now comes the little trick. So we take derivative d dk of this, and what we get is an equation which is just the following: rho of k plus rho whole of k is equal to 1 over 2 pi plus this Cauchy kernel that we have, star rho of k, okay, where, you know, so f star g, that's just the convolution, integral f star g of k, minus infinity to infinity dk prime, f of k minus k prime, g of k prime. Okay? So these are important equations. Okay, so this c, you remember, it's 1 over pi c divided by k squared plus c squared. Okay? Now, this functional equation here is the continuum limit, the infinite size limit of the beta equations. Okay? You have two functions here which are principal independent, rho of k and rho whole of k. Okay? But they are related by this single functional integral equation. Okay? So in principle, you still have one functional degree of freedom, which is once again your labeling for the beta states. Okay? So this is the, if you want, the first fundamental equation for thermodynamic beta ansatz for the Lieb-Liniger model. Okay? Is the derivation clear? Maybe the interpretation of this rho of k is a bit unclear, but maybe it will become clear later on. Okay? Yes?
Is there a way to prove that the k of x is invertible? So
yes. Yes, it's related to properties of this integral kernel, so I didn't take the time to do that. You know, it could take a half hour to do that. What you do is that it's an integral transform. You can give bounds on the eigenvalues of the operator imposing this integral transform. And the eigenvalues are all non-degenerate, they're all greater than 0, and they're bounded from above as well. Therefore, the operator is invertible in any regularization you would put for it. Okay? So it's okay. Okay, so these are the remnants of the beta equations once we've taken this limit of the infinite size. Okay. Let's say that we do that. So here you might say, but this is a bit bizarre because you told us that these beta equations are incredibly hard constraints on the rapidities. And now essentially you're telling us that the beta equations have boiled down to a single functional relationship between two functions, and that I am free to put any input, any single functional input in there that I want, and you will give me a solution. Okay, so that's the magic of the thermodynamic limit. This is absolutely correct. Take a pen, draw your favorite row of K, okay? And I will construct for you a beta eigenstate that has exactly this row of K. There exists an eigenstate in Hilbert space that will have a row of K that corresponds to the function you plot to any wished degree of accuracy. Once I take the limit L going to infinity. In fact, there will be an extensive number of states fulfilling this requirement. Alternately, you could say, well, all right, let me make your life more complicated. Let me actually give you a row whole of K. All right? So there's a slight annoyance here, because of course, if I look at the integral equation, if you give me the row whole of K, I have to work a little bit harder to find the row. However, I will be able to find a unique row fulfilling this integral equation, once again, in the thermodynamic limit, provided your row hole fulfills the simple requirements of being bounded between, so row hole divided by row total has to be bounded between 0 and 1. If this is the case, for any K on the line, there will be a unique solution for row of K. Alright? So what we've done really is that we've taken these infinite sets of chains that beta put around our necks and ankles, and we've said, alright, by going to the thermodynamic limit, we don't need those anymore. I can just do whatever I want. I write a row and I've got an eigenstate. Perfect. Okay? So this is the magic of the thermodynamic beta ansatz. Okay? So in a sense, the constraint is still there, but you've lifted yourself up by taking the thermodynamic limit. Okay, so we do that. You give me either a row whole or a row of K, and then you tell me, well, what are the properties of the eigenstate? Well, there are a couple of things you can write immediately. So given a row of K, the eigenvalues of the simple charges are, first of all, the number density, which is n over L in the thermodynamic limit. This is just the integral from minus infinity to infinity, dk of rho of K. Right? The momentum density, which is just the total momentum of the state divided by, again, the length. This is just the integral dk of K times rho of K. And you remember the expression for the energy. The energy was just the summation of K squared. So the energy density is simply integral minus infinity to infinity dk of K squared. That's a square. Rho of K. Right? This is a 2. Okay, so given such a state, you just have these eigenvalues for the simple conserved charges. Okay, I'm not going to have time to tell you too much about higher conserved charges in the Lieb-Liniger model. However, you can quickly understand that a very simple set of conserved charges is just to take the power sum polynomials of the rapidities. So summation over all rapidities of K to a certain positive integer power. And this gives you an infinite set of conserved charges, and this turns out to be a complete set for the Lieb-Liniger. But they're just slightly annoying charges, so leave that to private discussion. Okay, but number, momentum, energy, they're just the first 3 of an infinite set of conserved charges of the Hamiltonian.
You require them to be finite, each of them.
They don't have to be, yeah, so read our latest paper. There are physically meaningful states that have a finite energy density, but that have infinite conserved charges, the higher ones. Okay, but maybe then, before I leave at the end of the 6th hour, I will show you that explicitly. Okay. Right. So these are these simple values. And now the question is, well, what can we do with this integral formulation of the beta equations? Well, the first step, of course, is to look at simple cases. The simplest case, the most interesting state that we would like to characterize is, of course, the ground state. Okay? So let's try to focus on the ground state first. So, the ground state. Okay, if you think about it a little bit, then the ground state, its definition is a state with the lowest energy of all states in the Hilbert space. And how do you minimize the energy of the state in this functional language? Well, what you would like to do is essentially compactify rho of k as much as possible around k is equal to 0. Okay? You would like to put all particles as close as possible to the low rapidity sector, pushing all the holes as far away as is needed in order to achieve this. So this means that essentially we have three functions, right? Rho, rho whole, rho total. And rho total is the summation of rho plus rho whole. So what we would like is starting from an interval, starting from the point rapidity is 0 and moving outwards, we would like to identify rho particle with rho total. We want to fill every single mode in there, starting from the lowest energy modes. And we build it up like that. And of course, we are interested in states with a finite density. That means the little n is some number which we take to be of order 1 in the thermodynamic limit. And therefore, the support of this rho particle has to be finite. Okay? So we expect that the ground state is simply like a Fermi seep where we have filled everything up until a certain value of rapidity, okay, which we will write as kf. So the ground state essentially will be characterized by the following function. So there's going to be a rho of k, which is going to be equal to rho total of k for k less than some value kf and 0 otherwise. Okay? And conversely, the whole, the rho whole, is just going to be the contrary of this. Rho whole is going to be 0 up to kf. Then if k goes beyond these boundaries, kf, the rho whole will become rho total. Okay? So if we rewrite the beta equation for the ground state, what we get is the following. We have rho of k minus integral now from minus kf to kf dk prime. Our kernel C of k minus k prime, rho of k prime, is equal to 1 over 2 pi. And this is valid for k within this Fermi CKF. Okay? But now you tell me, okay, so you cheated us because what is this KF? Well, fine. Then I return the question to you. What is your favorite linear density of particles? Okay? Then you tell me n. And my tablet dies. You tell me n. Well, I say fine, n is equal to integral from minus kf to kf of rho of k. Right? So any given n that you want, I will just use as a constraint. So now essentially the system of equations that I'm solving, if you require a specific filling, is, first of all, I guess a rho. I solve this equation here which we will call the Lieb equation, although it actually carries an earlier name, which is much better because it's called the Love equation. So you can use that one in bar, you know the Love equation. And it's an equation that comes from classical electrostatics because it's the equation that you need to describe the capacitance of a capacitor made of two circular plates. Okay, so it's this is just from the 1940s and things. You get that. But the problem with this equation, of course, is that it doesn't have a closed form solution. Actually, Maxwell himself, in his original book, his treatise on electromagnetism, has expansions of solutions of this precise equation for the equivalent of small values of C that we have here. And this is quite complicated, which is why Maxwell did it. But anyway, so it's been looked at also in the 1940s, 50s. People started throwing numerical methods at this because, of course, it has extremely important applications to be able to describe, you know, these two parallel plate capacitors. Anyway, so that's it. So Lieb is kind of fortunate because yeah, he's got the equation named after him, although it's the Love equation. So yeah, go back to the problem. You want to find the ground state at a specific filling. Then what you do is that, okay, you say, well, all right, let me start maybe with a first guess. So I'm just going to put Kf essentially equal to pi times the density that you want, and then this rho here I'll take 1/2 pi, and then it's going to give me a first approximation here. But then I come to this equation here, and I notice that it doesn't quite fit. So then I solve this equation here with this initial, you know, starting from this initial guess. I find a solution, but then I go back to this equation here, and I notice that, oh shit, you know, too many particles. Therefore, what I do is that I just kind of rescale the function a little bit, so that's the right thing. I go back to this equation, okay, and then I just iterate like this, and I will very quickly converge to a solution. So in practice, you can very easily converge to the solution of this. But you do that numerically. Okay? It's very difficult to do. It's impossible to do analytically in closed form for generic C. Even if you, so the only case in which it's easy, so the only easy case is when C goes to infinity, okay? Because then the kernel C goes to 0, so the Lieb equation solved by rho of k is equal to 1/2 pi, okay? Provided you're in the region, so let's just write it as Heaviside function of kf squared minus k squared, right? So it's 0. So it's just you know, 1/2 pi over a certain interval, right? And then the kf is simply given by pi times the linear density that you have. Okay, so this is the only explicit solution that you can easily find. The small c solution actually is quite challenging to obtain. Okay, the small c limit, essentially, the rho of k becomes a semicircle, which goes into a delta function when you take c going to 0. Okay, but I'm not going to describe that for you. It's a bit of a challenge. Okay, so that's the way you do it for generic C. You just take your computer, you iterate a few times until you obtain the correct filling. Okay, and that's the way. If you go back to the original paper of Lieb and Linegar in 1963, that's exactly what they do. They give you plots of the rho of k for different values of the interaction. Okay, so I mean, I can try to sketch maybe just for your information. I don't know. You've already noticed that my drawing skills are not exactly legendary. But anyway, do this for YouTube audience. So no, that's terrible. Right, so in the C's infinity case, it's a box. In the smaller C case, what you obtain is essentially a shape that will start being round. Well, maybe it doesn't round off quite that fast. Ah, no, not that one. No. Yes. Okay, so in the lower C case, it becomes just a little bit more rounded off like this. And then when you get to the very low C limit, it becomes essentially like a semicircle centered around 0. So the KF, the Fermi boundaries, collapse to 0, right? And you get that. So that's why we kind of like to think of the interacting Bose-gas in 1D as being slightly fermionic in nature, because the way we view its ground state is as a Fermi C. Okay, but it's a Fermi C of rapidity, it's not of momentum, which are different things. Okay? Is that, okay, I mean, it's, yeah. Okay, so now what we can do is try to be a little bit more adventurous and look at other states in the Hilbert space. So what we consider are excitations in the vicinity of the ground state. So, excitations. Around the ground state. Okay? There are two things that we need to do here. The first thing will be to consider particle-like excitations. Okay, and so Lieb again in a follow-up paper to the first one. Actually, I'm not quite sure what happened there, because in 1963, Lieb and Lineker published one paper where they have the solution for the wave functions of Lieb-Lineker, a description of the ground state, and then immediately after, just back to back, there was a second paper which is just by Elliott Lieb about the excitations. But then if you read that carefully, you get to the acknowledgements at the end, and you know, he thanks loads of people, and then the very last thank is to Lineker for performing all the numerical computations, which is essentially, you know, a big part of the paper. So I don't know, I don't want to speculate, but anyway, so anyway, you will find these things. So Lieb in his follow-up paper essentially named these excitations, and this one is called type 1. Okay? So these are type 1 excitations. Okay, you could have thought of a more original name. You know, I guess it shows you that physics was more healthy in those days. Now people didn't have to come up with absolutely brutally idiotic names for new things. You know, reinvent the wheel and call it the roller. They didn't do that. They just called it type 1 and type 2. Everybody was happy. You know, glory days of academia. Okay, so let's consider particle excitations, and now what we're going to do is consider a state with quantum numbers as follows. Okay, we will take the ij to be equal to these things. Minus n over 2, minus n over 2 plus 1, etc., until we reach n over 2 minus 1. Okay, so this is like taking the n quantum numbers of the ground state and shifting them by a half integer. We have to shift them by a half integer because we keep periodic boundary conditions. And you remember, depending on whether we have an even or an odd number of particles, we go to the half odd integer or the integer lattice. Okay, so that's why we do that. And now, so this is a state with n plus 1 particles. There's a new quantum number, which is going to be n over 2 plus some integer, just call it m, okay, that represents a particle excitation. So you have added a particle on the right-hand side, positive momentum side of your Fermi C. Okay? So contrast with the ground state quantum numbers. Of course, are ij0 equal to minus n minus 1 over 2, etc., until n minus 1 over 2. Okay, so here there are n, and here there are n plus 1. N plus 1. Okay?
There is a slight mismatch.
Yes, there's a half integer mismatch between the two.
Okay,
Because
perfect.
if you have a certain parity of n here, say n is even, then this lattice automatically falls on the half-odd integers. If n is odd, it falls on the integers. And the other one, so if n was even, now n plus 1 is odd, so you have to go to the other sublattice, the other half-lattice. Okay, so the excited state has momentum. So this excited state, it has momentum P is equal to 2 pi over L times this M that we have. Okay? It will have rapidities, which we will just write as Kj. The ground state will have just rapidities that we'll write as Kj0. Okay, now what we expect. Well, actually, let me even be slightly more anally retentive here, because we have this set of Kj plus Q. Okay.
Sorry.
Yes.
Just a question. So we use this ground state for an particle like a reference state. Then we create this
Yes.
like one excitation.
Yes.
But why? We cannot use just the. I mean, we cannot just shift one quantum number.
We can. Then we create a particle Hall excitation. It's a choice. You're absolutely free to do that. Okay. So it is irrelevant how you construct your excitations, provided you construct all your excitations. Particle Hall excitations leave you in the same sector of particle number. Okay? So if you were to try to construct all your states in the Hilbert space with only this type of excitation, you would fail, because you would never be able to change the subsectors of Hilbert space with a fixed filling. These type 1 excitations, so defined, they're like creation operators. They allow you to hop throughout the Fock space. Okay? So it's a question of taste. Yeah. We can do it differently as well, because we could say we don't like this half integer shift. So what we do is we say, all right, all states with an even number of particles, they have periodic boundary conditions. All states with odd numbers of particles, they have anti-periodic boundary conditions. Okay? And that would just remove this half integer shift in there. It doesn't matter. Okay? Because both are individually complete. So you can do it whichever way you want. Okay? Here I'm actually following the precise conventions that Lieb had in his paper, just if you want to use that as a reference. Okay? But you don't have to do that. Actually, it's a nice exercise to do it a different way. Okay? Now, what we expect is that the difference between Kj and the ground state rapidity Kj0, that this will be small, some small thing. Okay, so we'll write this as dj, the displacement j, and we expect it. Well, I guess you can't see this is a big L, right? So this you expect it to be small, of order 1 over L. Okay? So the difference between where the rapidity, so you see you have your set of rapidities in the ground state, you put an extra rapidity somewhere, and because of the coupling between rapidities in the beta equations, there will be a slight reorganization of your set of rapidities coming from the extra interaction term that you have in there. Right? So this dj, this displacement, just quantifies this move that you have there. Okay, so what you can do is essentially subtract the beta equation for kj0 from that for kj. Okay, so essentially what you get then is the following. You get an equation for the dj's, which are then all coupled to each other, and then this dj is going to be equal to minus pi minus phi of kj minus q minus summation L is 1 up to the big N of phi of kj minus kl minus phi of kj0 minus kl0. Okay, so everybody understands. Okay, so Q, it's clear what it is, right? So Q is the rapidity of the particle you've added. Okay, so it's the rapidity associated with the quantum number n over 2 minus 1 plus n. Okay? Now, you see, we have that the displacements of the Ks due to the addition of this particle are very small. Therefore, this term here is also going to be of the order of the displacement between the particles. So we can just expand it, keeping the first order in 1 over L and tossing away the second. Okay, so expanding in 1 over L. Essentially what it tells you is that you just have dj is equal to minus pi plus phi kj minus q. Okay. Minus now 1 over L, the summation over all the 1 to n. And now it's just the derivative of this, which is essentially our kernel. Let me write it. 2c divided by kj minus kl squared plus c squared. Okay, that times dj minus dl plus order 1 over L squared. Okay, so this now, so what we've done essentially is that we've transformed the beta equations for the excited state relative to the beta equations for the ground state into a new set of coupled equations, but now for the displacements, for the dj's. And maybe it's a time to have a break. In the middle of the argument, let me just give you a 10-minute break and then so. Any questions about what we're doing now? It's kind of, well, you can think about it during the day.